Introduction to tensors. Now, tensors are used in many different contexts in physics. For example, the moment of inertia tensor is used to describe rotation of rigid bodies. For example, torque is equal to I alpha, angular acceleration. The stress-strain tensor, sigma epsilon, is used to describe elastic deformations. The conductivity tensor, sigma, is used in Ohm's law for anisotropic media. Maxwell's stress tensor, sigma, is used for electromagnetic forces. And in relativity, we have the metric tensor, G, which is used to describe space-time geometry. Now, as an example, we're going to concentrate on the conductivity tensor and Ohm's law. So let's recall Ohm's law in an ideal resistor. For a discrete circuit element resistor, the current that flows through the resistor, given in amperes, is related to the voltage that we apply across the terminals of the resistor, voltage in volts, divided by the resistance in ohms. So this is our discrete circuit element. So I is current in amperes, V is voltage in volts, and R is resistance in ohms. But if we have a distributed medium, we need to change Ohm's law to describe the distributed medium so that we have a current density instead of current, J, which is given in amperes per meter square in SI units, and this is equal to sigma electrical conductivity, which has a unit ohm inverse or mhos, meter inverse, multiplied by the electric field vector, which is in volts per meters. So this is our distributed medium, Ohm's law. So J is current density, E is electric field, sigma is materials conductivity. So this equation seems to suggest that there will be a current flow that is going to be in the same direction as the applied electric field with a proportionality constant sigma. So they will be parallel to each other. But however, we find that in some non-isotropic materials, sigma is crystal direction dependent. So we may apply an electric field in a certain direction. The resulting current density, for example, could be perpendicular to it instead of parallel. So these two quantities, two vectors, J, current density, and electric field vectors, they may not be parallel. Now, how do we handle this situation? To handle this situation, instead of writing this simple equation, we can write a matrix equation and say that we have components of the current density J1, J2, J3. These are related to electric field components E1, E2, E3 with this following conductivity matrix. The matrix elements are sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, sigma 3, 3. So in other words, we have this matrix equation. The J vector given in matrix representation is the sigma matrix multiplied by the electric field vector matrix representation. In other words, we can say that the ith component of the current density is sigma ij times the jth component of the electric field. And remember that this implies summation in Einstein summation notation. So if I open this up, this means J1 is related to E1. And how is it related? J1 is sigma 1, 1 E1. So sigma 1, 1 E1. Then I will have plus sigma 1 to E2 plus sigma 1 3 E3. So it depends on all of the components of the electric field. And similarly, I would have J2 equals sigma 2 1 E1, sigma 2 2 E2 plus sigma 2 3 E3. So I would have sigma 2 1 E1 plus sigma 2 2 E2 plus sigma 2 3 E3. So J1 is related to E1, for example, how? By sigma 1 1. J2 is related to E2 by sigma 2 2. All right, so this is sigma 1 1 and this is sigma 2 2. So basically that's writing this equation written in Einstein summation notation explicitly. We see these dependencies. For example, we can say sigma 1 2 describes the current J1 due to E2, and E2 is perpendicular to E1. Therefore, we would have the situation that we have described, sigma 1 2 is J1 due to E2, which is the current component that is perpendicular to the applied field. All right, so there is one complication here. The values that we have to put here depends on which coordinate system we work in. Sigma ij values depend on the coordinate system used. The conductivity tensor sigma, we show it with two lines on top of it, is defined as a new object that has both the elements of the matrix array and the basis vectors of the coordinate system. So that information is missing in the matrix representation. In the electric field matrix representation, we have E1, E2, E3 components, but no information on which basis vectors we have used. In subscript summation notation, this is EI, EI hat. Now I do have the unit vectors, the basis vectors that can describe the electric field. So it's a summation E1, E1 hat plus E2, E2 hat plus E3, E3 hat. Similarly, we can do the same thing for the conductivity tensor matrix representation. The matrix representation of the conductivity tensor is sigma 1, 1, sigma 1, 2, sigma 1, 3, sigma 2, 1, sigma 2, 2, sigma 2, 3, sigma 3, 1, sigma 3, 2, sigma 3, 3. But if I write it in subscript summation notation, this is going to be sigma ij, ei hat, ej hat. And what does that imply? It implies that this tensor is sigma 1, 1, e1 hat, e1 hat, plus sigma 1, 2, e1 hat, e2 hat, plus sigma 1, 3, e1 hat, e3 hat, plus sigma 2, 1, e2 hat, e1 hat, etc. And I can write this as sum over I from 1 to 3, sum over j from 1 to 3, I have sigma ij, ei hat, ej hat. So that's what we are writing here. So this is similar to the vector v, which is sum over I, vi ei hat, which is v1 e1 hat plus v2 e2 hat plus v3 e3 hat. So it's similar to it. So with that, Ohm's law with the vector tensor notation is written as the vector j is equal to the tensor sigma dot product with multiplied with the electric field, dot product with the electric field E. It's a dot product. Okay, so in subscript summation notation, if I try to write this equation, what would it look like? I have vector j. Vector j is ith component multiplied by ei hat. And remember, this repeated index implies summation. So it's j1 e1 hat plus j2 e2 hat plus j3 e3 hat. This is equal to the tensor sigma ij ei hat ej hat dot product with the electric field, which is ek hat. It's a vector. So this means this is going to be sigma ij ei hat ek. It's a dot product between ej hat and ek hat. And we know that the dot product produces Kronecker delta jk. So this is sigma ij ei hat. Here we have ek, and Kronecker delta jk, which means replace k with j. So we have sigma ij ej ei hat. All right. So this is telling us that because there are ei hats on both sides, each component of the current density ji is equal to sigma ij ej. So I have to go over the j index here. Sum over the j index, the I index remains. So j1 is equal to sigma 1 1 e1, sigma 1 2 e2 plus sigma 1 3 e3, etc. Okay, so if I write sigma dot product tensor dot product with the vector E, this is actually not equal to the electric field E dot product with the sigma tensor. And why is that? So let's take a look at this. For the tensor, I have ei hat ej hat dot product with ek hat. Now, is this equal to ek hat dot product with ei hat ej hat? Well, you can see that this is going to give me Kronecker delta jk ei hat. This is going to give me Kronecker delta ik ej hat. They're in different directions, therefore they are not equal to each other, which is to say the order in this operation matters. So we have to be careful with this. All right. So the tensor notation that we have introduced, this tensor matrix representation replaced by basically this notation, sigma ij ei hat ej hat, this serves the following functions. It establishes bins for the tensor components. So this ei hat ej hat thing is not an operation between these two unit vectors. It just describes to us the bins. So it's the ith bin, ith row, jth column bin, for example. Okay. It couples the components to a coordinate system, so whichever basis vectors that we use are here, it tells us that it's related to, these numbers are related to a coordinate system. It sets up the tensor algebra formalism the way we have shown here. For example, J vector is sigma tensor dot product with electric field, and it simplifies the transformations between coordinate systems, as we're going to see later on. Okay, so we have introduced the concept of tensors, which are used very frequently in physics. We have many examples, and one of the examples is the conductivity tensor, which is to describe the current density due to an applied electric field in an anisotropic medium. So that means the direction, there is a direction dependence for the current. In a discrete circuit element, we have V is equal to IR. That's Ohm's law but in a distributed medium, J is equal to sigma times E, and J and E, if they do not need to be parallel to each other, as in the case in non-isotropic materials, then we have to replace this equation with another equation that takes into account the possibility of having contributions to the current density in a certain direction due to electric field components, other electric field components. So sigma 1, 1 tells us the contribution from E1, sigma 1, 2, E2, sigma 1, 3, E3. And when we add them up, we get J1. So this is, in subscript summation notation, Ji is equal to sigma ij ej. Now, how can I describe this equation using my tensor sigma? So we find that the conductivity tensor can be written as sigma ij ei hat ej hat, so that the sigma ij is basically telling us the sigma values in the bins defined by ei hat ej hat. So this is the row and this is the column number. So as the electric field vector is ei hat, we have the conductivity tensor sigma ij ei hat ej hat. And this is basically, when I open this up, a summation over the indices I and j. You can see here it's a double summation over I and j. And similar to the vector v being sum over I, vi, ei hat. So with this, I can write the new the equation between J and E using the tensor notation, sigma tensor, where the sigma tensor is not just represented by a matrix, but it also has, using subscript summation notation, the basis vectors information. And I can double check this equation, sigma dot E. When I do that, I see that this is going to boil down to Ji being equal to sigma ij ej, which is exactly what I see in this matrix equation. So it seems to work very well. And one thing I have noticed here is that when you have a dot product between a tensor, second rank tensor, as we're going to see, with a vector, that is not commutative. So we cannot write the reverse and set them equal to each other. So the order of the operation matters here. And these ei hat, the way I have written ei hat ej hat, this is not an operation between these two unit vectors. It establishes the bins for tensor components. It couples the components to a coordinate system. The tensor algebra formalism can be set up with this new notation, and as we will see, it simplifies transformations between coordinate systems.